Hey, I'm Mel Strong, and this is a lecture on cloud formation and convection in the atmosphere. If you haven't watched the lectures on humidity first, go back and do that because we're going to be talking about dew point and relative humidity here. So, to recap, what we've been saying so far is if you take a body of air and you cool it down to its dew point, you will hit saturation. And as you cool it further, air molecules will come out of the vapor state and form drops of liquid on the surfaces that cool first. And the surfaces that cool first are the thinnest ones, which are usually grass. Now, the same exact process is happening up in the sky when we see a cloud. When you see a cloud, all that really is a blob of air that has been cooled down to its dew point. So the same process happens. The air becomes saturated. As it gets cooled further, water molecules must leave the vapor state and enter the liquid state. Now what's different is that on the ground, this happens on a surface like grass. So what's the surface up here? Well, there are these little microscopic particles in the atmosphere. You might know them as dust or smoke or soot, or these tiny little salt crystals where ocean waves hit each other out in the ocean and make sea spray. The sea spray evaporates and makes tiny little salt crystals that fly through the atmosphere. They find them all over above the continents. They're all over the place. And we call these things condensation nuclei because they're going to form the surfaces when water molecules come together. So here's an illustration of the sizes of the things we're talking about here. So here we have a human hair for scale. And first thing to point out is that the cloud droplets, the little spheres of water that are in clouds, are actually themselves microscopic. So a raindrop might be this size. We're not making raindrops here. We're making cloud drops. In the next lecture, we'll talk about how to get this. But for now, we're talking about how to get this, these two different size cloud droplets. Water vapor must form on a surface, and the surface it finds are these condensation nuclei, these tiny little specks that are in this diagram here. So we can look at some of these under a scanning electron microscope, and dust can mean all kinds of things. Usually they're fragments of rock, though, and so water molecules, when saturation occurs, they will start to condense on the surface of this dust particle. Or it might be pollen. Pollen has a lot of surface area, and so the centers of little cloud droplets are often pollen grains, or even bacteria. So there's bacteria in the atmosphere flying around, and water molecules will collect on the bacteria. Some of these are actually made by humans. So this is fly ash, and these little spheres of carbon, and they're made when you burn coal. And so coal power plants in this country remove most of that, but a lot of it still gets into the atmosphere, and water molecules will collect on the surfaces of these little spheres. So all of these things are examples of what condensation nuclei look like. So anytime you see a cloud, it's just air that's been cooled to below its dew point. And as humans, we can make clouds pretty easily by just adding water vapor to air that's already cold. So we do this, for example, on a cold morning. So this person is exhaling into cold air, and you can quote-unquote see her breath, which just means that her breath has been cooled to below its dew point. So for example, maybe the temperature outside is 40, and the dew point outside is 10. So we have relatively dry air. Well, think about the air that's in her lungs, right? So your lungs are warm and they're moist, and the air that you breathe in picks up a lot of water vapor from your lungs. And maybe the air that's coming out of your mouth has a dew point of 60, or maybe it's higher than 60. And the temperature of your breath won't quite be body temperature, but it's going to be pretty warm. And so you breathe out this air that's pretty warm and has a dew point of 60. Well, if the dew point's 60, all we have to do is cool it down to 60, and we'd start to make a cloud. Well, the temperature outside is 40, so as she breathes out this air with dew point of 60, as it cools down to 40, then that water vapor that's in her breath has to come out and form little tiny liquid droplets, and we see a cloud. Now you might notice that on some days you can see your breath, but it doesn't last long, like it's just an instant and then it goes away. In other days you can see your breath and it seems to linger for a while. So let's change this a little bit, and let's say that the day is the same temperature but the dew point is, instead of 10, is now 39. So notice that the dew point is pretty close to the temperature. If they were the same, relative humidity is 100%. They're not quite the same, but they're close. So what we can say without doing any math is that the relative humidity is pretty high with these conditions. Dew point's almost the same as temperature. On a day where the relative humidity is really high, your breath will linger in the air longer. Because remember, relative humidity is related to evaporation. If I have low relative humidity, I have a high rate of evaporation. So in the first example, when the dew point was 10, her breath might not last very long at all because the evaporation rate is so great that those little droplets are quickly evaporating. In this case, because the relative humidity is high, her breath will linger in the air much longer. So if you see, you have a morning where you can see a big cloud around people when they're breathing and it seems to linger in the air, one of the things you can learn from that is that the relative humidity must be pretty high on that particular day. Also, and this is harder to see, but this one picture kind of shows it, there will be a gap between the person's mouth and when the cloud forms. And the reason for that is the air that's coming out of their mouth is pretty close to their body temperature, and you've got to cool it down to the dew point, and it takes a little while for that to happen. So there'll be a little space here where there's no cloud until we finally hit the dew point right there, and then the air is continued to cool further. Now there's another way that we add water to the atmosphere, and that's through burning fuel. So hydrocarbons are a class of molecules, and they get their name because they have carbon and hydrogen in them, and they're pretty much all flammable, and we as humans burn them. So the simplest possible one is a gas called methane, also known as swamp gas. If you can't tell, that's a swamp. And methane's flammable, and if I light it on fire, it reacts with oxygen in the atmosphere, and it produces CO2 that goes back into the atmosphere, and it also produces water vapor that goes into the atmosphere. Or if I take a slightly more complicated hydrocarbon, propane, so it's more complicated because it's got more carbons in it. So C3H8, propane is the gas you might use in your barbecue, but when you burn it, you react it with oxygen in the atmosphere, which then adds CO2 back to the atmosphere and also adds water vapor to the atmosphere. Or I can get more complicated and get a molecule called butane. Butane is C4H10. This is what they put in lighters. You react it with oxygen, produces CO2, and produces water. So in each one of these examples, as we burn this fossil fuel, we're adding water to the atmosphere. More and more complicated hydrocarbons not only become more complicated molecules, but you can get mixtures of things. So for example, gasoline is a mixture of different kinds of hydrocarbons. Coal is a mixture of different kinds of hydrocarbons. So one example of this is when you start your car on a cold morning and you see this big, what looks like a big white cloud coming out of your tailpipe, in fact, is a cloud. It's water that's coming from the burning of hydrocarbons. So there's water vapor coming out of your exhaust pipe. It gets cooled to the dew point, and condensation occurs. And the other thing you might notice on a cold morning when you're sitting in traffic and you're behind somebody else is you'll see water actually dripping out of the tailpipe. And that's water that's from burning of hydrocarbons, burning of gasoline. It reaches the dew point somewhere inside the tailpipe because it hasn't warmed up enough yet and drips out, and you can see it running out of the tailpipe. Another example is if you see a coal-fired power plant. So this is the Navajo generating station in Arizona, and so they're burning coal. And on the cold morning, you will see a big plume of white coming out of the smokestacks, and that's all water. As you burn coal, it produces water, like we've been saying. The water vapor comes up into the atmosphere, chills to the dew point, and you're making a cloud, and the cloud eventually evaporates. Another example is with planes, and a plane will often leave what's called a condensation trail. So this jet engine's got 4 of them. Each jet engine is burning hydrocarbons, and as a result is producing water. Water vapor comes out, and at first it's hot, and you see there's no cloud right here. There's a gap, and then eventually it gets cooled to its dew point, and you get a cloud, and there's 4 clouds for the 4 engines. So condensation trails whether you might notice that some days condensation trails are very obvious and they stay up in the sky a long time. And some days, if you look carefully, there are planes that actually don't have any condensation trails at all, or they're very short. And that's all dependent on what the relative humidity up here is. The higher the relative humidity, the easier it is for a jet to make a condensation trail. So here's some condensation trails. And on this day, it looks like the relative humidity is pretty high, because one of the things that can happen is that condensation trail can actually start to nucleate into clouds. So this one is starting to turn into cirrocumulus, right? This one's starting to turn into cirrocumulus. Down here, looks like some of these are starting to turn into cirrus. So remember, clouds, really high clouds are typically all ice crystals. And so one of the things that condensation trails from jets can do is they can basically make artificial clouds. They'll make little tiny narrow bands of cirrus or tiny bands of cirrocumulus. Here's a very interesting satellite photo taken one morning where the relative humidity was pretty high on that morning. And you see all these streaks, all these little white streaks all over. Those are all condensation trails from jets. So what we're working up towards is we've got some little puffy clouds here. And what we want to do is understand, why is it that this cloud forms right there and ends right there? And why is there a cloud here and not a cloud there? That's what we're working up towards. But what we're going to do first is get into a little bit about properties of air. So we're going to spend a couple minutes looking at the properties of air. And I've got a simulation from PhET called gas properties. And what I've got is a big empty box here where all of the air has been removed from the box. We just have two gas molecules. So this might be, say, nitrogen and oxygen. We just got one of each. And what I want you to notice is that, notice the behavior of these air molecules inside this box. They move in a perfectly straight line until they hit something, and then they reflect off. So if we can imagine taking all the air out of a room, and when we release, say, two molecules, an oxygen and nitrogen, what we would notice is that they would go flying out, and at room temperature, perhaps a couple hundred miles an hour. They go flying out and start bouncing off the walls and the objects in the room. Now, realistically, of course, there is way more than just two air molecules. So what I'm going to do is I'm going to add a bunch more molecules to this box. So I'm going to add some small ones. And then I'm going to add some big ones. And what I want you to notice is that in addition to bouncing off the walls, they're actually more bouncing off each other now. And this is more realistic to how air actually works. If I had one individual oxygen or one individual nitrogen, even though it wants to move in a perfectly straight line until it hits something, what it actually does is it moves in a perfectly straight line until it hits one of its neighbors. And then reflects off its neighbor, and then it moves in a perfectly straight line again until it hits another neighbor. And as it's moving these little straight lines, it might be going several hundred miles an hour in each one of these little movements. But over time, it takes a really long time for it to actually get across the room because it has to balance against all of its neighbors. But that's how to imagine air. That's how to imagine how air behaves. Imagine a room full of ping pong balls just flying around the room, bouncing into everything. Okay, so now imagine that you are this little guy here and you are pushing, this is a wall that can move, slides back and forth, okay? And he's got to push on that wall because these air molecules on the other side are pushing back at him, right? And so for every square inch of surface, every object, everywhere on Earth, there are air molecules that are coming down and hitting that object. So on this, you can see them, they're bouncing up, bouncing against the wall several times a second. In real life, they may be hitting every surface millions of times a second. And that produces a pressure, and that pressure is what we call air pressure. So in this particular simulation, there's a gauge here of air pressure, and they're using a unit that says ATM, and that's called atmospheres. So in this little simulation, 1 atmosphere, just to put in perspective, is how much air pressure you would feel at sea level on Earth. Okay, so it doesn't really matter. The exact numbers or anything doesn't matter. And the temperature in this case is Kelvin. And again, the exact number doesn't matter. What matters is we're going to make a few adjustments. I want you to look at how these two things change. So our little guy here can push against this wall. So I'm going to push the wall in and make the box smaller. And so what I want you to do is keep an eye on those two things. So here we go. So I'm going to push. And as I push, notice what the temperature is doing and notice what the pressure is doing. Okay? So the pressure has gone up and the temperature has gone up. And also, the air molecules are moving much faster than they were before. And we've said this in an earlier lecture that temperature is a measure of the average speed of a gas. So in the atmosphere, as we make it warmer, all objects start to move faster. So I'm going to open up the box and notice pressure goes down, temperature goes down, and the molecules are going slower and slower and slower. Okay, so this is one of the big properties of gases. If I have a closed box, or think maybe more like a balloon of air, and I compress this air, right? If I compress the air gets warmer and the pressure goes up. And if I expand my box or expand my balloon, then the pressure goes down and the temperature goes down. So there's one more thing I can demonstrate here. And so far, the behavior of the gases in this box is what you would get if there was no gravity. And what this simulation allows you to do is add gravity. So what I want you to do is imagine that this box now represents the Earth's atmosphere. Okay, so this entire box is all of the air in the Earth's atmosphere, and Earth is down here. And what I'm going to do is turn on gravity. And I want you to watch what happens to the air molecules in this box. So here we go. Now notice, first thing you can notice is that the denser blue gas molecules are concentrated towards the bottom, but actually, and it's harder to see this with the red, but all the gases are actually concentrated more towards the bottom. So this is the way to visualize air in the Earth's atmosphere. Because Earth has gravity, gravity is trying to pull all the gas down to the surface. And the only reason that all the gases aren't just laying on the ground is because they have enough kinetic energy that they bounce against each other and continue to stay in the atmosphere. If Earth had a stronger gravitational field, it would be able to compress the gas closer to the surface. So what this means is if you were to, say, get into a balloon and you were to rise up into Earth's atmosphere, there would be fewer and fewer gas molecules banging against the surface of the balloon because most of the gas is concentrated near the surface, near the ground. And so on Earth, what we know is that air pressure is highest at sea level. And as you go up and up and up, as humans, it gets harder and harder to breathe, right? So in Albuquerque, we're a mile above sea level. A mile above us, you are about the top of Sandia Crest. And up there, a lot of people have trouble breathing. By the time you get up to, say, Mount Everest, you're 30,000 feet. Almost nobody can breathe. And so air pressure decreases with height above the ground. And this is why. Because Earth's gravity is trying to pull the gas down towards the surface. So when we talk about things convecting in the atmosphere, we use this term called air parcel. And an air parcel is just a blob of air. You can't see it. But when you hear that term, just think of a balloon. So here I've just got a normal little balloon. And as we just learned, air pressure, you can think of air pressure as being the result of all those little air molecules banging against the side of any surface, including the outside of this balloon. Now, there's also air on the inside of the balloon, and there's air pressure on the inside, and the molecules on the inside of the balloon are also banging on the sides trying to get out. And it turns out those two forces are balanced, so my balloon does not change size, right? So The forces pushing in and the forces pushing out from inside are exactly balanced. When we talk about air parcels in the atmosphere moving up and down, I want you to visualize a balloon just like this that's moving up and down. So I'm going to put this balloon in this little chamber here, and what I'm going to do is I'm going to start pumping the air molecules out from inside this chamber. So in other words, the amount of air in the balloon itself is not going to change. The air around the balloon is going to change. And this is going to simulate what happens when a balloon or a parcel of air rises up into the atmosphere. As it rises up into the atmosphere, there's less and less air molecules up there that are banging on the sides of our little balloon, so there's less pressure up there. So this is going to simulate that. I'm going to pump air out of this chamber. So this little tube, you can't see it, but there's a pump off the screen here. So I want you to just imagine there's air being sucked down this tube, and we'll see what the balloon does. So again, this is a simulation of what would happen to an air parcel as it goes up into the atmosphere. Okay, so we are now pumping air out of this balloon, and I think you can see that it's getting larger. And I'll step out of the way here. Okay, so I'm going to turn off the pump. So I don't think I need to convince you that the balloon got bigger. So this is what you have to keep in mind, which I want you to imagine when we talk about air parcels rising into the atmosphere. As they rise into the atmosphere, there's less air banging on the outside of the sides of this balloon or the sides of an air parcel, and the air parcel will expand. So anytime air rises from the Earth up into the atmosphere, it expands and it gets larger. Now, what I'm going to do here is I am now going to let air back in, and so we're going to see, so we would expect that the balloon should get smaller. So let's see if that's what happens. Now, in a face-to-face class, what I do at this point is I pull this out and I hand it to somebody in the class, and I ask them, tell me how it feels. And they grab it and they're like, oh, it's really warm. In fact, the balloon is pretty hot right now. And the reason for that is because I just took a balloon that was the size of this and shrunk it down to the size of this. And as we saw in the earlier segment, when you compress air, it gets warmer. The opposite is also true. If you expand air, it gets cooler. So even though I can't really demonstrate it to you here, when we expanded that balloon up to the size of this whole chamber, it was the air inside there was actually cooler. So put those two ideas together. If I have a parcel of air and it rises into the atmosphere, okay, two things happen. It expands, and because it expands, it cools. On the other hand, if I have a parcel of air and I'm bringing it down, it gets smaller and it gets warmer. Okay, so we got to keep those two laws in mind. So not only do we know that rising air expands and cools, and sinking air compresses and warms, but we can predict exactly how much the temperature will change. Turns out it doesn't matter where you are in the atmosphere, rising air will always cool at a rate of 5.4 degrees for every 1,000 feet that it rises, or it will warm 5.4 degrees for every 1,000 feet that it sinks. Or in the metric system, the temperatures will change 9.8 degrees Celsius for every 1 kilometer. These numbers are known as lapse rates, and this particular number is called the dry adiabatic lapse rate. And dry means that the relative humidity is less than 100%, meaning you're not in a cloud. So these numbers are valid for air moving up and down the atmosphere as long as it's not in a cloud. Adiabatic is a little bit more hard to understand, but if this is my air parcel As it rises up or down in the atmosphere, remember it can change its temperature. It's going to expand or it's going to compress, and the temperature is going to change. Adiabatic means it's not absorbing any extra heat from its neighbors, or it's not emitting any heat to its neighbors. In other words, adiabatic kind of means it's insulated. So we're going to be talking about these air parcels moving up and down the atmosphere, and we're going to pretend that they're perfectly insulated from their environment. That's what we mean by adiabatic. Okay, so for this next part, I'm going to use a handout that I have put up on Learn for my current students, and if you're from somewhere else on the internet, it's on my webpage, and you might want to print this out so you can kind of follow along with what we're going to do. It's two-sided, and we're going to start with day 1. So the premise of this is that we've got a mountain up here in the atmosphere, and we've sent a weather balloon up, and the weather balloon has measured the temperatures every 1,000 feet. So we know the conditions of the air above our heads. Now, we'll talk more about this in a future lecture, but when you have a mountain that's sticking up in the atmosphere, the surface of the mountain will warm faster than the air. Okay, so we've got 3 locations here where we know the conditions at the surface, the temperatures and the dew point of the air at the surface of the mountain. And the question is, will the air at those 3 locations rise? And if it does rise, will it eventually form a cloud? So what I'm going to do here is start with the one on the right and get a calculator. So here we know that the temperature is 85 degrees, the dew point is 55 degrees, and the question is this air going to rise? And I check the conditions of the air right next to it, which is 84. Well, 85 is greater than 84, and air wants to rise. Now, you've heard the term warm air rises. That is true, sort of. If I have a blanket, a continuous blanket of warm air, it will not rise because any parcel within that blanket is the same temperature as its surrounding neighbors, and it doesn't rise. But if I have a little plume of warm air that's warmer than the air around it, then it does want to rise. Okay, so in this case, 85 warmer than 84, it's going to rise. So what I'm going to do is I'm going to draw some arrows to represent this air rising. Okay, now, question is, when it gets 1,000 feet above the ground, so as it rises, it expands and it cools, what is its temperature up here? Well, from the dry adiabatic lapse rate, I know it's going to cool 5.4 degrees Fahrenheit for every 1,000 feet. And in these exercises, we're sticking with Fahrenheit and feet because America, that's why. So I'm going to take 85 and I'm going to subtract 5.4 and I get 79.6. I'm going to draw it right on the line because this line, the temperature right on that line is 78. So I compare, is this warmer than 78? Yes, it is. So it's going to want to continue rising. So now I draw more arrows, and I want to know, okay, what would its temperature be if it got up to this height? So I'm going to subtract another 5.4, and I get 74.2. And I look and I compare, is it still going to rise? 74.2 warmer than 72? Yes. So it's going to continue to rise. I subtract another 5.4, and I get to 68.8. Now, warmer than the air around it here, warmer than the air around it here, warmer than the air around it here, but here, 68.8 is cooler than 70. So what we know is that our parcel of air will rise and expand and cool, and rise and expand and cool, but stays warmer than the air around it until it gets to this point. That means somewhere between here and here, our rising air stops. So, and we don't know exactly where. So in this class, for convention, let's just draw it in the middle. So in the middle, this air turns and starts to sink back down like this. So it doesn't get this high, right? We know it passes this point, doesn't get to this point, stops somewhere in the middle. This loop that we made is called a convection current, okay, or a convection cell. And it has another popular name called a thermal. And thermals are outside right now every day as long as the sun is up. So what happens is the sun comes up in the morning and the surface starts to warm, and depending on what the surface is made out of, it warms to slightly different temperatures, and little plumes of warm air start to rise. You can't ever see it, but it's happening every day. Now, what will happen is early in the morning, the thermals rise maybe just a few feet and then they sink back down. By late afternoon, they may go up several miles before they come back down. Now, birds know all about this, and a big bird with a big wingspan, it takes a lot of energy for it to flap its wings for active flight. So what they'll do is they will figure out where there's a thermal. So right now we got this big guy up here, and he has found a plume of rising warm air. And so what he has to do is, if he stays within this plume of warm air, he doesn't have to flap his wings, because he can just kind of use that rising air as lift, and he can stay up as long as he wants. Now, one thing that the bird has to take into account, though, is in this case, in the one that we drew, he can fly in here, no problem. But the problem is for him is that if he gets out here, he's going to get sucked down this arm of the thermal. And of course, he has a bird brain, so he doesn't know this. So if you watch these big birds, what will happen is that they'll be flying around, and then they accidentally fly into this part, and suddenly you'll see them just kind of suddenly dive, and it looks like they're diving down like they're going to crash into the ground, but then they'll figure out how to get back into the thermal. Okay, so let's do the next one. And the next one, surface is 76, temperature up there is 72. And the question is it going to rise? 76 warmer than 72. So yes, it does. So I'm going to draw some arrows. And the question is now, okay, what's the temperature 1,000 feet above the ground? I take 76 and I subtract 5.4 and I get 70.6. Is that warmer than the air that's up there? So the number I'm checking with is this one. That's what the weather balloon has measured. Yes, it's warmer just barely. So let's do it again. Another 1,000 feet, subtract another 5.4, and I get 65.2. Warmer? Yes, it is. Keep going. 59.8. Warmer? Keep going. So I'm drawing arrows this whole time to show that the air is rising. Subtract another 5.4. I get 54.4. Still warmer? Yes, it is. Do it again. Subtract another 5.4. 49. Now, at this point, 49 is warmer than 48, so we know it's going to rise, but there's something else that's going to happen, because it turns out the dew point was 49. So our little air parcel that has been rising and rising has finally cooled until it hits the dew point. So right here, temperature is now equal to the dew point. And what's the relative humidity conditions when that happens? Relative humidity is 100% right there. And we get condensation starting at this point, and we're going to start building a cloud. Okay? Now, before we go to the next step, realize now there's actually another thing that's going on. And we talked about this in a previous lecture where we said that when you hit the dew point and you start making dew, that the water molecules not only collect into liquid droplets, but they bring in these little boxes of thermal energy and they release them. And we call that latent heat. And the formation of dew, we said at the time, helps actually keep the grass warm when it occurs. Well, we're now doing the same process, but we're doing it up in the sky, and we're doing it around those condensation nuclei. So as our water molecules are coming in to grow a little cloud droplet, they're adding thermal energy to the cloud. Okay? So there's two competing processes then. As this air wants to rise, it's going to expand and cool, right? That's process number one. Process number two is, as we condense water, the water is adding latent heat back to the air. So number one cools it, number two warms it. Who wins? Well, the rising air cooling still wins, but what it means is that our lapse rate is now different. Instead of 5.4 degrees every 1,000 feet, it's 2.7. And it's actually varies on a bunch of things, but in this class, we're just going to use the number of 2.7. And so this number 2.7 has a couple of different names, sometimes the wet adiabatic lapse rate, or the saturated adiabatic lapse rate, or the moist adiabatic lapse rate, but all three of these mean that relative humidity is 100% and you have a cloud. Okay, so just to recap, it's rising and expanding, which is cooling, but the latent heat that's being added is warming, so the net result is it's still cooling, but not cooling as much as it was before. Okay, so let's return to our cloud here. So from now on, because I'm inside a cloud, I'm going to subtract 2.7 instead of 5.4. So 49 minus 2.7 is 46.3. Okay. Is it warmer than the surrounding air? Yes, just a little bit. So I'm going to draw my arrows to show the air rising inside the cloud, because that's what happens. So we're going to go up another 1,000 feet, subtract another 2.7. I get 43.6. So my cloud is growing. And we're making a little cumuloform cloud, like maybe a cumulus. Okay? 43.6, warmer than 43. So I keep going, and I try another 1,000 feet. So I subtract another 2.7, 40.9. Okay, 40.9 is colder than 42. 43.6 is warmer than 43. So we know that it gets past this line, but does not get to this line. So what I'm going to do is I'm going to draw my cloud kind of like this. I'm trying to show that it gets somewhere between those two. I'm just going to draw it halfway. Well, where does the air go? Well, the air exits out the top of the cloud, and it goes back down. Okay, so our convection cell is the same thing as the thermal. It's just that this one cooled enough that it reached the dew point, and so it started to build a cloud. And so what we're doing is we're just testing every 1,000 feet, and we can figure out, we know where the bottom of the cloud is, and we know where the top of the cloud is. The other thing this means is that you actively have to have air moving into a cloud to keep that cloud alive. We'll talk more about that in a little bit. So on this worksheet, there are 3 points on the front on day 1, and then on the back there are 3 more points for day 2. So I'm going to stop right now with this, and I'm going to make a separate video where I work out all of the points on both day 1 and 2 if you're having trouble understanding what's happening here. Okay, so let's return to the initial question, which is why do we have clouds in certain locations and not others? Why is the bottom of this cloud here? Why is the top of this cloud here? So we can answer some of these questions now. And if I look out on this landscape, I can see that there's different elevations and there's different types of vegetation. So we've got bushes and trees and grass and whatnot. And so as the sun comes out, it warms all these different materials to slightly different temperatures. And the locations that are warmer are sending up thermals, sending up plumes of warm air. And some of those plumes of warm air sink back down without making a cloud. But everywhere where you see a cloud, you have to imagine that there's a plume of warm air that has risen up to a certain point where the temperature is equal to dew point. And then from that point forward, you will have made a cloud, and it continues to rise inside the cloud. And if we annotate the whole thing here, so air is heated at the surface, rising air expands, expanding air cools, hits the dew point, air is saturated, you have 100% relative humidity, air continues to rise inside the cloud until it is no longer warmer than the air around it. It exits out the cloud, sinks back down. Okay, so that's happening under each one of these little cumulus clouds. Now there's a couple of words to describe these conditions. If we say we have stable air, what that means is that if I try to make air rise, it sinks back down to its initial position. Also, if I push air down, it wants to pop back up to its initial position. If you have stable air, and this is a term you'll hear maybe in a weather report sometime, if you have stable air, that means that the skies will probably be cloudless, or you might have some little tiny cumulus clouds. The opposite of that is unstable air. So if we have unstable air in the weather report, what that means is that if the air rises, it's going to want to continue to rise, which means it will probably likely hit the dew point and make a cloud. So when we have days of unstable air, we often get tall cumulus clouds or cumulonimbus clouds. And we'll talk more about this in the next lecture. So to summarize what we've done today, a cloud is just air that has been cooled to the dew point. So if it happens at the surface, we get dew on the grass. If it happens up in the sky, we get a cloud. The surfaces that the water molecules collect to are called condensation nuclei, mostly just dust. The gravity of the Earth wants to hold all the air to the surface, but it can't. So what happens is it holds most of the air towards the surface, which means that the air pressure is greater towards the surface and decreases as you go up. So therefore, if you have a air parcel and it goes up, it feels less and less air pressure. It expands. Expanding air cools. Every day when the sun comes out, you get these rising plumes of warm air that are rising, expanding, and cooling. And if they go high enough, they may cool to the dew point, and that will get you cumuloform clouds. So in the next lecture, we'll talk about what happens if this process continues and the clouds continue to grow. I'm Mel Strong. Thanks for watching.